I mean, if okay, okay, so now the traditional neural networks do not have this persistence capability that the human brain has. So what it majorly lacks is that it just looks at every moment the way it is. It does not have contextual information or past state information and does not take it forward from there. So that's like a major shortcoming considering all the use cases and the applications that we have. For uh, the commonest way that you can look at it is, I mean, every single thing that I say is contextual. It is sequential. It makes sense only if you see it in a cumulative format. It would make zero sense if you just uh, take one word at a time. So now, to give you an example, imagine if you want to, if you're going through, if you want a neural network, if you want to design a neural network for a video, and for different frames in the video, you want to classify the events that are going through at different points in time. Now, the problem is that networks are required. The problem with traditional neural networks is that they will just look at that frame in that frame. So if you are trying to do this for a movie per se, if you are doing like you are say generating captions, or you are generating some kind of analysis on a movie or a documentary with different frames involved, then you cannot really have a very realistic and accurate So for such systems, it is quintessential that you would require a sequential learning based system, and that is where recurrent neural networks really come into the picture. Now, if you see on the right here, this is basically a standard architecture, or to say that this is basically how it looks. So here A is basically the input, and xt is basically to a neuron. Xt is the input and ht is the kind of output that we are expecting. And as you can see, there's an iterative loop over that. So this doesn't end with just one iteration of it. So if we look at recurrent neural networks in that sense, then a recurrent neural network is basically just a normal neural network that does the same operation iteratively. So my neuron will take inputs and it'll work in an iterative manner. So it'll process every single input on the basis of the input and the contextual information, and then give an output for that, an output state for that. So that's how it typically looks. Now, if I can change the slide. Now, if the loop that I showed in the previous slide, these loops basically make recurrent neural network a bit mysterious looking. However, if you think a bit more, it turns out that they aren't all that different. It's just that they are many normal neural networks placed beside each other, and if you follow that kind of a sequence, like the one that you can see here on the screen. So this iterative loop, if you break that down into multiple neural networks, that's what a recurrent neural network is. Now, if I mean, another thing that I would like to add to that previous slide is it's like more of a chain like structure that a recurrent neural network follows. And if it makes any sense, then if you take the example of the word hello, and if I give, say, H to this neuron, now, because that's the first state, it doesn't have any pretext or any previous state information. So that'll be taken as it is. Now, if we go to the next one, it'll have the output for H, and then E becomes the next letter. And that's processed along with information about H. So that's how this chain like a structure unrolls and follows, and that's how it is processed. Now, if we look at now, before I mean, just to contextualize the whole thing and bring it into context, let's look at a few applications of RNN, a very few naive applications of RNN, so that it makes more sense to you. So. One of the most typical, I mean, two of the most typical applications is sentiment analysis and image captioning. So image captioning, basically what we do in image captioning is you are trying to generate a caption out of an image, as the name very name suggests. So you are trying to identify what's going on in that image. And then you're trying to find or identify text that matches that feature, or the set of features that have been segmented or identified from the image. So that's basically finding out text, determining text. Now, generating text is sequential in its very format, because words will need to have semantic meaning, and that's where RNN comes into picture. Another one is sentiment analysis. Sentiment analysis is like when, for example, if there are a lot of reviews in a product on Amazon, and you want to analyze how many positive and negative reviews. Now, what is going to decide what's a positive review and what's a negative review? What you're trying to do is you're trying to analyze the text that is there, use a vocabulary that identifies positive words and distinguishes them from negative words. And on the basis of the presence or the absence of such words, you give a positive or a negative classification to that particular comment. And on the basis of a cumulative analysis of these comments, you can say the degree or the percentage of positive reviews that you received on the product. So that's basically the kind of applications that this particular neural network has. Now, going on to how do you basically, I mean, if you just see these two diagrams on the screen, then your general feed forward neural network, which is a standard neural network, what it does is that it has an input layer, it has an output layer, and it has a hidden layer. So when you give the input to the input layer, it basically just takes in the input, passes it on to the hidden layer. The hidden layer performs the activation onto the input and finds an output. So output is basically the class to which your input belongs. That's your normal feed forward network. Now, what happens in a neural network, a recurrent neural network, is that you have multiple hidden layers. So it's no longer about just the input going to a hidden layer and getting the output. It is input going into a hidden layer, which will perform one layer of one iteration of activation on it. Then the output from that hidden layer will go to another hidden layer, which will perform another set of activation on the output from the previous layer and generate another output. So this series of activations that the hidden layers will perform onto the input will determine your output. And that is how we say that a recurrent neural network is just a rolled in forward neural network. Or if you roll out the recurrent neural network, you will what you'll have is a number of feed forward neural networks. Okay, now if you take a look at this particular diagram, the now the main thing about I mean activations and the designing of the neural network lies in the biases and the weights that you decide for the different hidden layers. Now, these have to be different for all the different hidden layers because of the kinds of activations that you're performing. On the basis of the kind of application and the activation that you're performing, your weights and the biases will consequently differ. And hence, each of these hidden layers would behave in an independent manner. So that's how it's like a rolled in feed forward network, because all of these hidden layers will perform a different kind of activation, will and um, skew your input towards the output or steer your input towards the output in its own different way. So they are all independent layers in their own context. So when you combine all of them together, and and then you decide to have the same weights and the biases for these hidden layers, that is when you come to this kind of an output, which is there on the right. So now what we've done is we've combined all these layers together. We've put in a common weight and a bias in these layers, and all of these hidden layers are rolled in together into a single recurrent layer. So this is one single recurrent layer. Now what it's doing is, what you are doing is you're supplying an input to the hidden layer at all the different time step. Weights of the recurrent neuron would be the same, since now you just have a single neuron. You don't have multiple, what do you say, you don't have multiple hidden layers. So a recurrent neuron basically stores the state of the previous input, and it combines it with the current input, and thus preserving some kind of a relationship between the current input and the previous input. That's how the state of the input is maintained in case of a recurrent neuron. Now, if we try to dive a bit deeper into how a recurrent neuron basically looks, and just look at the details of these, then it's basically, if we take a simple task, let's go back to the hello example. So what the hello example basically is doing, it's basically processing each character. So it's doing character level processing. So considering that, I mean, if you assume this recurrent neuron to be a character level, RNN structure, then if we have the word hello, so we provide the first four letters, say we provide the first four letters HELL, and ask the network to predict the last letter. So that's the job that we have given the recurrent neural network to do. So here now the vocabulary for the task would be the four alphabets: HELO. This is what the vocabulary for this neural network would be. Now, in a real case scenario, this is just for example's sake, in a real case scenario, when we're working with proper natural language where you have complete sentences and a complete vocab, then your vocabulary, the vocabulary on which your recurrent neural network is working, is the entire English language vocabulary, if you're working with English language, obviously. So that would be like taken from the Wikipedia. So it's like a complete repository of vocab that's infused into the model to ensure that it understands the meaning and the semantics of and the usage of the different words that are there. Now, if we try and just understand how the structure on the screen would basically process or predict the fifth letter, which we wanted to do. So if we've given four alphabets, HELL, and if we want this recurrent neural network to predict O, then what is it that it will basically do? Now, in here, if you see the blue RNN block here that you can see on the screen, that basically performs a kind of a recurrence formula, if you say, because mathematically, if you look at this, it's basically a recurrence formula that has to be applied onto the input to get the output. So the blue block here basically applies the recurrence formula to the input vector and the previous state information, which is provided by the form of this particular loop that's given here. So now, in case we start with the letter H, now H is the first letter, there's no preceding state. So that will go unaffected, untarnished, I would say. If you take the second letter, which is E, so at the time when E will be processed, the letter E has a previous letter already in place, which is H. So the processing of E would not be just processing of E, it would be processing of E along with the information that the preceding letter was H. And subsequently, everything, the recurrence formula occurs for every single time step. So when you get L, you just don't process L, you process L along with the contextual information that the preceding letters were H and E. So that's how you come to the point where you can predict a particular letter when you're processing O. For example, when you're trying to predict O, you know that the previous letters were H, E, L, L. So on the basis of the vocabulary, the set vocabulary that we have, what is the most, what is the probability that the next letter will be a particular character. So that's basically, that's how internally the system works, where it calculates the probability of a character being the next letter, and the one which is the highest probability will be your recommendation or the prediction that the system makes. So that's the kind of reference formula that's generally applied here. Now, let's quickly take a look at what are the different things that RNNs can do. RNNs basically have, I mean, if you just do a simple Google search, the most common applications that you would find for recurrent neural networks would be around textual information, natural language processing, NLP tasks, and with the whole thing about sentiment analysis, and the use of sentiment analysis, not just for general applications such as Amazon review, or review analysis or something like that. There are so many other applications of sentiment analysis that have been discovered lately. For example, analysis of sentiment of tweets for a person can be used to identify mental health issues or depression. So many healthcare, government related applications, as well as business applications, which was the base why most of this was created. And there is a range and a plethora of applications that are already in place for all of these natural language tasks. Now, at this particular point, particularly when we talk about natural language processing, a special type of RNN is typically used for natural language processing, which is LSTM, long short-term memory. Now, the reason why LSTM is used for these particular tasks is because you remember we spoke about the hello example where we wanted to um, predict the alphabet O. Now, what you have to understand is that processing of every single character, for the processing of every single character, the state information that can be saved doesn't the system doesn't have infinite memory, so it can probably just store uh, the last few alphabets, or maybe a last few words. So what happens is, as you move on, um, state information about characters or words that were much farther away behind the particular character or word, the state information is lost. This is what is called long-term dependencies. So as the distance from the character being processed or the word being processed, as the distance from that word increases, uh, the gradient basically begins to vanish. So you lose that information, you lose the state information associated with those words, and they no longer have an impact on um, the prediction of the next character or the next word. The problem that this causes is something that we look in the future slides, but just to give you an overview, the problem is that your context becomes very limited now. See, if your state can only store, in my case, if in the hello example, if it can store state information for HELL, it will most probably predict O correctly. But if it can only store contextual information related to LE, then the next character can be anything. It can be T, it can be let, it can be AN, lean. So it can be anything. So the probability of getting higher accuracy reduces as the vanishing gradient problem increases. So that is the problem that generally occurs with NLP tasks. And in order to deal with that, a special type of RNN is used, which is LSTM. And we're going to talk about that in a little more detail as we go on. Uh, Now, few of the NLP tasks that are very commonly, solved using RNNs and LSTMs is include extractive and abstractive summarization, both of which have been my research topics for a long time. I had my PhD, and most of my work was around the use of LSTMs with attention layers for extractive and abstractive summarization. What you do as part of that is you analyze the text. So if you have a body of text and you need to summarize it, say in a sentence or in a couple of sentences, why would you want to do that? The reason you would want to do that is, for example, I mean, if you've seen research papers, then a research paper typically has the body of text and it has an abstract and the keywords. Now, in all probability, uh, the abstract and the keywords are a true reflection of the body of the text. So if there's a way that you can automatically extract this or automatically generate abstract and extract the keywords, then that would make tasks simpler, the task of research paper writing simpler, and the task of reviewing the paper also simpler. So for applications like these, what we require is extractive and abstractive summarization. Extractive summarization is specifically what that does is it extracts a specific significant keywords or words on the basis of some kind of a score, which can be semantic, which can be calculated using different kinds of methods. So there are graphical methods, neural networks are used for this purpose. So all kinds, I mean, there are a lot of heuristic based as well as artificial intelligence based methods for extractive text summarization. So what you do is you calculate a specific kind of score for the main words, and on the basis of a ranking of those words, you extract the highest ranked words as the most significant and cite them as key phrases. Now, for in case you want to generate an abstract automatically from the body of text, you cannot extract words for that because if you've seen keywords are specific phrases or words, and it's not like a long sequence. Uh, on the contrary, your abstract cannot be directly extracted sentences from the body of text. So what you'll have to generate is you'll have to generate natural language in a way that it makes sense. So such kind of summarization techniques are called abstractive text summarization, where the system goes through the body of text and generates a text that's a summary of the text. There are specific methods for that, typically deep learning and recurrent neural networks, specifically LSTMs. LSTM with attention are used for this purpose. LSTM improves the vanishing gradient problem, and LSTM with attention further improves the kind of contextual information that a particular neural network has. So that's basically, I mean, that's like an overview of the natural processing tasks that are generally associated with this. Summarization being one of such tasks. You have a lot of other tasks like sentiment analysis, which are very well established fields that totally work around this. Then the second one here is machine translation. So machine translation basically is when you have um, when someone speaks one language and your system taps that language in the form of text, your system then converts that into another language. So what you're doing is basically you are converting a language of variable length, a natural language text of variable length in one language into a variable length text of another language. So it's a very complicated task for, I mean, for natural language processing, in the sense that both of these, it needs to understand one language and it needs to generate semantically correct other language. Let me just quickly check the messages. I mean, okay. Okay, right. So that is the kind of task that machine translation and and applications related to that are generally concerned with. Then other than that, there are a few more applications which include if you see here on the screen, which is image captioning or image description determination is one of the most popular. Uh, it's a use case that involves both CNN and RNN, in the sense that you first need to analyze the image using CNN and then use RNN for generating this kind of a natural language based caption. So it uses both CNN CNNs and RNNs to perform this task. And as it's very it's pretty intuitive that you just identify the main objects which will be converted into your nouns, the activity that is being performed which will be converted into words, and then you need fillers which are articles and prepositions or conjunctions that can make that are just to make sure that semantically the sentence or the description makes sense. So that is the kind of variables that are associated with image captioning particularly. Now other than that, other than what I've mentioned, there are two more applications which include speech recognition and time series prediction. Speech recognition generally deals with identifying audio signals, converting them into natural language text, and then analyzing it. So that's speech recognition or voice-based systems. And voice-based systems is basically an application that's based on speech recognition. Then the other one is time series prediction. Now, because time series data, like I mentioned in the previous session as well, time series data is sequential data. Where, for example, if we talk about weather data, um, the weather the parameters, particularly I mean whatever parameters related to the gaseous composition of the atmosphere, or the temperature readings, or pressure readings, or moisture readings, all of these are done at a periodic basis. So depending upon what the periodicity is set at, if say you are taking hourly readings of temperature during the day, then it's a sequence that follows, right? If you look at it from a larger data set perspective, for example, if I collect temperature readings for one complete year, now saying that the temperature was high in a particular month will not make sense unless you have a relative value to say that it was higher than what, or it was lesser than what, it was lower than what. So this context of this relativity that's associated with time series data is what makes it sequential, and that is why it becomes a use case of recurrent neural networks. Now, let us look at the various types of recurrent neural networks. So basically four types: one-to-one, one-to-many, many-to-one, and many-to-many. Now, starting with the ones that are on the screen, which are one-to-one and one-to-many. So basically, and what happens in the one-to-one thing is you just have a single input and you have a single output, which is like your general machine learning problems that you have. Then one to many is you have a single input and you have multiple outputs. For example, uh, your image captioning. Your image is a single input. What you are getting as output is a series of words, a sentence or a phrase, which is multiple outputs. Now, in the previous case, which was one to one, for example, image classification that we did for CNN, it's like a one to one thing where there's one input, which is the image, and the output is you give whether it's like class A or class B. So image classification or any kind of classification that just has a single input and a single output is falls into the first category. Second one, a typical example is image captioning, where you have a single image as the input, and what you get as the output is a series of words, which is multiple output. Now, the other two are many to one and many to many. So in many to one, what happens is that I mean, as the name suggests, it's many inputs giving you a single output. Now, sentiment analysis is a classic example of this, where you analyze a particular, say, a review comment for a product on Amazon. So it's like a review is a body of text, and the output is whether it's a positive sentiment or a negative sentiment. So the output is single one, your input is many, so many to one. So that's why it's called a many to one RNN. Finally, it's many to many, like the summarization problem that I was talking about, where you have a body of text which has many inputs coming in, and what you're generating is again many inputs, many outputs, but of a variable length. So variable length input, variable length output. That is what makes a classic case for many-to-many RNNs. Now, talking about the vanishing gradient problem, like I mentioned, what happens is as you travel through the different words and the different characters and the different inputs that the RNN gets to process at different time frames, what happens is that you tend to lose information. So if say I started at step 1 and I've reached now step 15, and my buffer value can probably store information related to 5 steps, then when I'm at step 15, I have information from step 10 to step 14, but I have no or minimal information about step 9 and before that, steps before that. So that's basically, I mean, in a very naive way, that is the vanishing gradient problem. Now, recurrent neural networks basically allow you to model the time dependent and the sequential nature of data problems, particularly, for example, such as stock market predictions, for example, machine translation, and text generation or the text summarization that I talked about. However, what happens is that it's still hard to train as far as vanishing gradient is concerned, because you really, I mean, it's really very application dependent to understand how much of a gradient and how much of a vanishing or exploding gradient is allowable for a particular application. And in order to find workarounds and customize RNNs and LSTMs for such applications, multiple research pathways have come along where people have added an attention layer into an LSTM to improve the long-term dependencies, in the sense that it allows you to hold more information about the context so that you can get a semantically correct sentence as output, and you just don't get any jumbled set of words that make no sense. So that's what this is about. Other than that, there's also, I mean, I vaguely mentioned about the exploding gradient problem. Uh, what happens in the exploding gradient problem is, while you're training the neural network, if the slope tends to grow exponentially instead of decaying, in the sense that um, if the error gradients accumulate in such a manner that it results in a very large update to the neural network in terms of biases and weights, then the model weights during the training process go off completely, and the gradient explodes. So that's the exploding gradient problem. Now, what happens as a result is, one, your training time will increase. Second, your performance will deteriorate. Your accuracy will deteriorate. So these are the problems that are generally associated with the gradient problem, and this is why I mean, it's particularly important, and it's very, very significant for textual applications, because I mean, in a very naive term, if I say a sentence in a particular order, say I say hello, how are you, it would make sense. But if I jumble up the words, if I say you and then how and hello and are, then you would have to shuffle it to make sense out of it, so it would not make any sense. So all of these gradient problems, or problems related with dependencies and problems related um, with storage of contextual information, lead to jumbled up words. Or I mean, at the character level, if it's hello, then all the alphabets of hello would be jumbled up, so it would not make any sense semantically. And you want your systems to be as semantically correct as possible, so that, I mean, that's the objective, right? To generate natural language. And natural language is semantically correct, and that is what gives it the meaning that it has. And that is not possible unless I mean, all of these problems are sorted out. Now, going on to the next. Now, this is a quick overview of the gradient problems and how it affects a d- the RNN in general, and what is it that we generally do to deal with them. Now, what is it? What is the problem with long-term dependencies? As I briefly talked about. Now, one of the biggest reasons why we're studying RNN here is because we want, we want to connect the previous information with the correct information, and that is what the task is here, such as previous video frames to understand the present frame. So, if RNNs could do this, they'll be extremely useful, but it really depends. It really depends on how long, in terms of time frame of a context, you require in order to have a better understanding. Now, sometimes we only need to look at recent information to perform a particular task, and that is the kind of variations that occur. That, sometimes, for example, the start of a sentence. If it's the start of the sentence, you probably don't need contextual information about what happened before this start of the sentence. So sometimes you need a lot of contextual information, like if it's like the last word of a sentence, you need contextual information about the whole sentence. So it really depends. Now, the problem is that it really depends on how much of a contextual information you require, and this increases the complexity of RNNs that we need to design for these purposes. Now, if for example, if you're trying to predict the last word in say the clouds are in the sky. Now, we don't need any further context or previous context other than what is required here. So the problem with any any kind of application that we try and model using RNNs is that it's very context specific, and the context time frame really depends on the application. Now, in in case, I mean, if you take a few variations in, I mean, the previous example, you did not really require a lot of context. But if I give you another example, say I grew up in France. I speak fluent. So if I want you to predict the last word, you can predict French only if you know the previous sentence and the context. So I grew up in France, and that's why I'm fluent in French, right? So you can't be any other language. For this, contextual information from the previous sentence is also required. So the problem with most of these applications is, and the complexity and the rise in complexity of these is because of the kinds of applications and the kind of variations that occur within uh, a body of text that we're trying to analyze. Now, in theory, RNNs should be and are completely capable of handling very long-term dependencies, and there should not be any reason that they should not be able to do it. Um, for example, I mean, from a very humanly perspective, if you see, a human could pick parameters to solve specific problems, and then you can give those parameters, and it should work fine. But in practice, RNNs don't seem to be able to learn all of this in the way that we expect them to. And a large part of actually deep learning, the problem with deep learning architectures is because we are simulating the human brain. um, we know what the input is, we know what the output is, but the kind of processing that happens within those layers, the interaction between those layers, is something that makes the output unpredictable at times, and of the nature that even the person who designed the network cannot really control the output. So that is why we don't really know why some of the things happen the way they happen. So in theory, on paper, RNN should be completely capable of handling long-term dependencies. However, because of the interactions that happen within the layers, RNNs don't practically seem to learn those dependencies as well as we expect them to. Now, in order to deal with these issues, what we've come up with is LSTM. So LSTM is like the full form of this is long short uh, term memory. So it's usually just called LSTM everywhere, and it's nothing but just a special kind of an RNN, which is capable of learning long-term dependencies. So it was totally and specifically designed for this purpose. Um, and the beauty of these architectures is they solve a lot of the problems that RNN has, particularly for natural language processing. So they are basically designed to remember information for very long periods of time, and time that is practically in a way that that becomes their default behavior. So long term dependencies, understanding them, retaining information about them, and understanding them to the degree that they can use that contextual information to make any future predictions is part of the default behavior. Now, all microneural networks now have, you can say, a form of a chain of repeating modules of neural networks like we discussed previously. However, in standard RNNs, the repeating module will just be a simple structure. So it'll be like just this as you see. But with LSTMs, this is a more complex structure where we replace the standard structure with a chain-like structure to give it more capability and allow it to handle the input in a more special way. Now, without worrying about the details of this, and it's, I mean, if you're interested, you can always go to any book on deep learning and RNNs in particular, and you should be able to get a hang of this. So it's not really something very, um, I mean, easily accessible thing. Now, the next thing that I wanted to talk about is the core idea behind LSTM, and why is it that we why is it the hype that it is. The key to LSTM basically, as we've been talking all through, is the cell state. So if you imagine it in the core computer science context, then you can just see it as a state diagram where your current state is dependent on the previous state and the input to give you the output. So that understanding of that state diagram and implementing that into the deep learning architecture is all that LSTM is doing. Now, cell state here basically is you can see that as a conveyor belt of sorts, which runs down straight through the entire chain with only some kinds of linear interactions as in the form of the mathematical operations that we saw in the previous slide. So it's just flow of information from one layer to another with a series of chain-like interactions that happen in between. Now, the LSTM does has the ability to remove or add information to the cell state, so you can regulate what goes in and you can remove information that's not required. What that helps you do is it helps you improve the amount of relevant information that the RNN, the core RNN of the LSTM will hold. So how they do it is using gates. So gates allow you to control the kind of information that will be held as part of the cell state. Now the sigmoid layer basically is what outputs numbers between 0 and 1. So that describes how much each component should be led through. So that I hope I'm audible to everyone. I mean, I think my internet connection is a little unstable. I hope I'm audible to everyone.
Yes, ma'am. Now, okay.
Okay. Okay, so just to take you through a walkthrough of the LSTM architecture, the first step in LSTM is to decide what information we are going to throw away from the cell state. So, what information at the gate level will be included or not included. The decision is made using a sigmoid layer called the forget gate layer. Now, it looks like if you can see here, if you can see the formula here. So what it basically represents is 1 would represent that it should be kept completely, and 0 would represent that you should get rid of it completely. So the gate basically works on a binary system, 0 or 1. For information that needs to be included, the value is set to 1, otherwise it's set to 0. Now, if we go back to our example of the language model trying to predict the next output based on the previous ones, in such a problem, the cell state might include, for example, so for example, if you are predicting if you say she is going to the park to take her daughter. So now, if you see, you need to learn the pronoun to predict her. So her and his, if the choice is between her and his, then you should choose her because the pronoun that preceded it was she. So specific information about the pronoun needs to be saved as part of the cell state, and which is what the gate allows you to do. Now, all of the other information that was there was not really required for predicting that particular output, and that is why that's how LSTMs improve the efficiency and performance of RNNs, particularly for sequential information. Now, if we look at the next step, it is to decide what new information we are going to store in the cell state. So this has basically two parts. First is a sigmoid layer, which is called the input gate layer, which decides which values will be the values that we are going to update. And next is the tan H layer, as you can see here, which creates a vector of the new candidate values. So you basically just add these values to the state, and in the next step, what we do is we basically just combine these values together to create an update on the state. So if we go back again to the example of the language model that we've been taking, we would want, say, to add a few more information uh, about, say, the gender, and replace it with the previous information that was there. So if there's an update, then that update is made during the second step. Now, the cell state is updated in step number 3, which allows you to understand the previous steps that have already decided what was to be done when, and now we actually implement it. So in step 1 and 2, you decided the gates, the information that you require now, and the update that needs to be made. In step number 3, you actually made that update. So that is the difference that comes along in step number 3. Now, if again you go back to the language model example that we've been taking, this is where you would actually drop the information about the old subject's gender. So any previous information that you had about gender would be dropped, and you would use the current sentence context to update the gender value for this particular layer. Now, finally, in this, what we need to decide what we are going to output. So the output will be based on what? It will be based on our cell state, but it will be a filtered version of that. So first we run a sigmoid layer, which decides what parts of the cell state we are going to output. Then we put the cell state through this tanh to push the values between -1 to 1. Now, then we multiply it with the output of the sigmoid gate so that we only output the parts that we decided to output. So we find, first we decide the gates, we decide which information needs to go through the gate, then we update the cell state. Then after that, we finally decide what is the output that we need for that particular example. Now, for the language model example again, now since it just saw a subject, it might want to output information relevant to a verb, or if it's like if the word is in the next might be a verb, or if it's something related to a conjunction, if it's joining with two sentences or clauses, then it would context know that a conjunction is required at that place. Now, there are several variants of LSTMs, and if we just quickly look at this, and in the context of what we've already discussed, uh, LSTMs are different in the way in their versions, in a way we can say that. So the differences are minor. It's not a major difference. LSTM generally is a popular overall variant, but there are minor differences in terms of the kinds of researches that have been done on LSTMs. And this one is basically what the one that you can see on the screen basically just adds peepholes to all the gates. And there have been many papers that have been published around this, where adding of peepholes to gates to allow infusion of information on choice basis is it's like a version of LSM that's in use. Now, another variation is the coupled forget and input gates. So what this allows you to do is, uh, instead of separately deciding what to forget and what new information to add, all of these two decisions of deciding and forgetting can be done cumulatively as part of this LSTM structure. So we only forget when we are going to input something, when we know what's the replacement that we have for it. Now, this is a slightly more dramatic version of LSTM, which is also called GRU, or if you've heard about it, gated recurrent unit. It combines the forget and input gate into a single update gate. So now the update is done singularly. It's not a multi-step process as we previously saw. And there have been several papers around it, several research papers around it that you can, have a look at if you are interested. Now, looking at the use cases of LSTMs, and before that, a few business applications as well, is the basic applications that we discussed, like text summarization, have specific business applications, like report generation, for instance. So, or if I take the example of research papers, then if I'm able to, automatically generate a summary of a paper that has come in for review to me, then it's easier for me to understand if it falls into the scope of a journal or a conference. So things like that, where you can use summaries of documents to quickly go through them without having to go through the whole document, are some of the very common business applications associated with recurrent neural networks. Now, besides this, another very common application that has recently come up is around conversational interfaces, where you have, for example, you have a lead generation scenario where you need to gather information about a potential client, or while a customer support scenario is designed to assist customers with product use. Now, to be able to analyze the sentiment of the person who's on the other side of a bot or on a conversational interface, and accordingly updating information in terms of natural language to give responses, is another use case of RNN. Now, other than that, RNNs, I've discussed quite a few applications already. If I directly come to the use cases that you can see here on the screen, there I have provided these two, workshop files in the form of Jupyter notebooks. They can be used for, one is for stock prediction. Stock prediction is time series data, like I mentioned, and in the given model, it's using an existing model to train stocks data to make a prediction on what can be the possible values of stock prices, etc. So that's one of the use cases. The second is text generation, which is a character-based text generation. So this is not a word-based text generation. This is character-based text generation, and it's also using a pre-trained model. So you can quickly go through these, but both of these, if you'd like, to see how RNNs basically work, and make variations in terms of batch sizes, in terms of epochs, in terms of functionality, and what are the kinds of variations that you can make is something that I've provided in a Word file, so you can try all of them. Now, to quickly give you a walkthrough of the files that I've shared in terms of code, um, if I can stop sharing now, I can probably do a reshare. Mhm. Okay. Okay, let me just share my screen. Okay. Okay, so I hope my screen is visible. So this is the, I mean, if someone can please confirm.
Yes, it's visible, ma'am.
Yeah, okay. So this was the first use case which I had given for CNN. So I mean, if you take a quick look at the code, then the first part is just including the libraries. The second is because the data set is available in the form of a multi-folder format where you have 6,000 images for 10 categories. So getting the data set ready in a form that it can be used as training and test data is something that's pretty complicated for this particular example, and this is what this code basically does. So it unpickles the data set that's available in the form of a zip file. Now then this part basically just divides the data into training and test data. Then you pre-process the data. um, as part of pre-processing, the three main tasks that are being done is one, for every single image you convert it into a flow 32 representation and then normalize it, and then finally perform one hot encoding for it. And then after that, once that's done, you build a model, and so you basically give the training and test data to the model. uh, these are the model specifications. So this is a pretty simplistic model that we've implemented for this particular case. For most image applications, it's typically seen that a technique called augmentation is used. Now, why that's the case is because we generally don't have a lot of image data, and even if we have a lot of image data is generally the reason why we don't have a lot of image data is because it's generally memory intensive and takes up a lot of space. So what is done is we generate multiple images from a single image and use that to train a deep learning model. Because if we train a deep learning model with lesser data, the chances of it overfitting are higher. So that's why generally what happens is we take an image, create multiple translations, multiple versions of it. So if, for example, I have 10 images, I create, say, 10 versions of that image, and of every single image that's there. So that converts 10 images into 100 images for my training data set. So that's how augmentation of data allows, it basically allows us to exemplify the data set that's available for training, just to make sure that the model doesn't overfit. Then finally, we compile the model and train the algorithm. So you can probably see the accuracy. It's pretty low here because this is going to take a good amount of time to train. I've just done it for 3 epochs. You can increase the number of epochs, and the accuracy will improve. So this is something that you can give a try to. Then the second example for CNN was sentiment analysis. As you can see, first part is like just adding the libraries. This is because NLTK is the standard toolkit that Python supports for natural language processing, and for most of the pre-processing tasks that you're going to perform, like removing punctuation, removing stop words, removing words that are shorter than a particular length. And why do you need that is because, for words like articles, a, an, etc., you can remove these are not semantically important words to make any predictions. So to filter out words like these, you have specific functions and packages, functions available in this particular package. So you can directly call upon them, and it just simplifies stuff. Then after that, this is the part where you read the data set. So the data set is available. I mean, I have given this TSV file as part of the folder, so you can access that. Then cleaning data is all the pre-processing that you will need to do, like removing punctuation marks, removing top words, removing anything that you don't really require for this particular application. Then you split the data into training and test data. This is a standard train model that we're using for training this model. So this is something that you will have to download, because that's like a heavy set of data data set. So you will need to download this and put it into the same path as your Jupyter notebook for it to be accessible. Or otherwise, I mean, give the absolute path and make sure that you're giving the right path for it to detect it. Finally, tokenizing and padding is done. Why is that done? Because as you probably know, when we're working with textual data, we basically represent words with this specific codes. Now, every sentence doesn't have the same number of words, but when we're trying to train the model, we need a fixed length vector to train the model. So what we do is we choose the maximum, the largest length that we have for any sentence in the whole body as the input shape for the model, and then we convert all of the sentences that we have into that shape using padding. So, for example, if my maximum length is 10 words long, then and my current sentence just has 7 words. So I will use codes for the 7 words and use a padding code for the rest 3, just to make sure that all the sentences are a fixed length vector that goes into the input, because the input requires a fixed length vector. Now, then finally, we define the CNN, which you can see here. Again, it's not a very complicated CNN. It's pretty simplistic. You can find a summary of this here. So you can see all your convolution and pooling max, pooling layers, and all the just different layers that make up the CNN model. And you train it, and you can finally see two kinds of accuracy. One is the validation accuracy, another one is the test accuracy. So that's the second use case. Then for RNN, again, there are 2 use cases. One is stock price prediction. Uh, the data for this is something I've provided. Again, you include the libraries, you divide the data set into training and test data. You will have to do a feature scaling for this, just to make sure that your data is lying in the scale that you desire. Then you define the model here, run it for, and you can run it for a good number of epochs. It's not going to take a lot of time because the data set is relatively smaller. And that's how those are your results. So this again, there are a few variations that you can try with this, and I've given that as part of the Word document. The last one is the character level text generation using RNN. Uh, Go back again, you start with the setup, you download the data set. This automatically downloads the data set, so you don't have to do anything. For the RNN use cases, you don't really need to download anything. For the CNN use cases, you will have to download, for the first one, you'll have to download the CIFAR data set. The link for this is again given in the Word document. And for the second one, sentiment analysis, you will need to download the Google Word to Vec model. So a link to that is also provided. Then here you again read the data, you process the text. Let me find a way to scroll down. Okay, now you do normal text processing. You define the model, convert it, split it into test and training data. You build the model, compile it, find the accuracy. So that's basically what you are going to do for um, every single of these use cases. Now, in this particular use case, a specific function that you're going to find is the one step function. So why we have this particular function is because we are doing character level prediction here. So it's working one character at a time. So when you're making up the word, you're going to run this one step function multiple times. You're going to call this again and again to make that prediction, make up the whole word. Now, again, because you'll need to train it for a good number of epochs to get a very good accuracy around it. So don't freak out if it doesn't work as well for like 3 5 epochs. So you'll need to work a little more on the number of epochs and wait and sit and wait and go have a coffee and come back for it to have the accuracy that you desire. So that's basically all I have from my side. If you have any questions, I'll be happy to take them. Am I audible?
Yeah, yes, madam. Hold on, ma'am. I request all the participants, if you are having any doubts, please interact with the ma'am.
Otherwise, I mean, just to conclude in a more
All the participants, could you please switch on your video? We will have a photograph with Khan madam, Samiya Khan madam. All of you, please switch on your video.
Ma'am, can you share your mail ID, please?
yes, I can do that. Should I write it in the chat?
Yeah, ma'am, please.
That's my email ID.
Yeah, thank
Yeah,
you. Thank you very much, ma'am.
on there.
Thank you so much, madam. Thank you so much for your elaborate lecture as well as the hands-on session, which is more beneficial to all the participants. I request all the participants, please go through the hands-on session. Document is going to share to all of you. So please go through that. Google Colab, already you are having the experience. Since 2 days we are operating with the Google Colab. Now I request Samiya Khan madam, as a token of gratitude, we are awarding a small digital award to you. So please accept the award.
Thank you very much. Thank you. Thank you very much for having me, and it was totally my pleasure. Thank you.
1 minute.
So, ma'am, like identifying the drawing, recognizing the drawing, can we do it how we have done using, we have done, you have explained the character recognition. Is it possible?
Yes, you have a. In fact, I mean, if you do a quick search, there are a lot of CNNs already trained for character recognition or object recognition. So you can actually use. You can look through GitHub. If there's already a code available, you can just customize the code according to your problem, and it's not very complicated. It's pretty simple. So solve your problem.
Okay, thank you.
Okay, madam. Share here. Madam, please accept our digital award.
Thank you very much. Thank you very much. And it was a pleasure. And
Please consider our thank note also.
thank you very much. And I hope it was useful to everyone. And I hope it will take you forward in whatever research you're pursuing presently.
Thank you, madam.
Okay, right.
Okay.
Thank you.
Bye.
Okay, bye-bye. Thank you.
Okay, thank you, ma'am. Have a nice day.
Thank you so much. Bye-bye. Take care.
So now, thank you to all the participants. We came to the end of the day 4. So today we completed 3 sessions. First session is pre-processing of medical images. There we learnt about the denoising and fusion techniques by Deepika Kundal madam. And after that, deep learning for computer vision by Samiya Khan, University of Wolverhampton, UK. And third session is deep learning for text and sequential learning by same Samiya Khan. So with these 3 sessions, we completed day 4. Tomorrow we are going to have the last day, that is the day 5. Day 5 first session is exploration of 3D reconstruction. There we will see the techniques for 3D data, how to handle 3D data with deep learning. That is a new emerging technology trend we are going to see. After that, we will see hands-on object detection and tracking with the optical flow technology, optical flow method by Senthil Kumar sir, Associate Professor Amrita Coimbatore. And last session, hands-on applications of CNN, face mask detection and sign language detection by Mr. Madhu, CEO of MadBlogs. So these are the 3 sessions we are going to have by tomorrow. And tomorrow we have to take the exam. During last FDP, they took the exam at 7 o'clock. Now it's your choice if you want to take the exam after the third session or either at 7 o'clock. That's your choice. You please give your choice. Based on that, we are going to conduct the exam. Will you write the exam during after 4:30 or after 7?
What will be the duration, ma'am? How many questions it will
Half
be?
an hour, 20 questions, 25 marks. All are multiple choice questions, 20 questions, 25 marks. That's the pattern.
So after the test, so eligible participant, when they will get the
Madam.
certificate?
60% you should get in the examination, 80% attendance. These are the 2 criteria any attendee has to satisfy to get the certificate from the ATAL.
So it will be
like this 80% attendance, 60% marks in the examination.
So the certificate will be sent to mail ID or in the login we have to download. How it will be, ma'am?
You need to download your certificate from your website, madam, ATAL website.
Okay.
ATAL people only giving, madam. From the ATAL website you can download.
Okay, ma'am. Thank you.
I think 2 days it takes, madam. We have to upload attendance and marks, everything. Then only after uploading these 2, you have to submit the feedback form. Then you can download the certificate. You are going to get the certificate by Tuesday.
3 to 4 days. It will take the 3 to 4 working days, madam. After submitting all those documents from our side, they are going to be verified. After that, we can able to download your certificate through ATAL website. It will take 3 to 4 working days. Coming back to the exam, many of them are willing to write the exam at 7 o'clock because during 4 to 4:30,
some
very
may
few
be
members
commuting, mutation. They may leaving the colleges. Last time that was the representation we got. That time is the closure time, so many people may leave for homes. That's why they opted 7 o'clock as the exam time. Will you take the same?
Duration half an hour, ma'am. 7 to 7.
Duration is half an hour.
7 p.m. madam. Yeah, madam,
Okay.
it's good to take the exam at 7 p.m.
7 it will be good, ma'am, because we
yeah.
have college.
Many of them are also asking to conduct the exam at 7 o'clock. So we'll go for that 7 o'clock, madam. 7 to 7:30 or 7:35 is the actual exam time.
Okay, sir. One more thing, can we get these Jupyter codes for ma'am?
Sorry?
A Jupyter code for my last session.
Jupyter code.
Yeah.
Jupyter Colab, sir.
I,
Jupyter Notebook or Google Colab.
Yeah, Jupyter.
So you are asking the code. That means NIT from NIT Warangal, J. Ravi Kumar sir has been taught that session.
No, sir. Right now, this is final session for Sanya ma'am.
Okay.
You need that document, sir. We will share, sir.
Okay, ma'am. Thank you very much.
Madam shared. We will see and we will share.
So whatever the documents madam has been shared, we will share to you, sir. Today.
Yeah, sure. Thank you very much, sir.
Along with the attendance form, we will also share those documents also. Just please find it.
Okay, thank you, sir. Can we leave, sir?
Yeah. You can leave, sir. Thank you.
Okay,
Thank you all.
Thank you, sir.
Have a nice time. Bye. All the best for your exam.
Thank you, madam.
Okay, thank you, ma'am. Thank you.
7 o'clock.
Thank you, ma'am.
Okay, take care. Bye. Thank you, ma'am.